let's take a look at radioactivity. First, we're going to consider why nuclei decay, and then we're going to consider how they decay. Why nuclei decay goes back to the concept of stability in a nucleus. So remember, a nucleus is stable when there is a balance between the attractive strong force between all of the nucleons and the repulsive Coulomb force between the protons. We can also think about it in terms of the binding energy. A nucleus is more stable if it has a high binding energy per nucleon, because that means that it requires more energy per nucleon to rip apart the nucleus into its separate nucleons. Now, a nucleus which is less stable, with less binding energy per nucleon, can decay into a nucleus with a greater binding energy per nucleon, a more stable nucleus. Now, when a nucleus changes to a more stable nucleus, it emits energy in some form, and this is called radioactive decay. I'm going to write down the reaction equations for a few types of radioactive decay, a few examples of radioactive decay. So for example, carbon-14, it can decay into a more stable nuclide called nitrogen-14, and when it does that, it emits energy in the form of something called a beta minus radiation. It's an electron and an electron antineutrino. Carbon-11 can decay into a more stable nuclide called boron-11, and when it does that, it decays by something called beta plus radiation, and that is a positron and an electron neutrino. Radium-226, it will decay into the more stable radon-222 by emitting an alpha particle, and cobalt-60 will decay into a more stable form of cobalt-60 by emitting a gamma ray. Now, I am not going to explain exactly what these particles are right now, but we'll come back to this. It's important to say the decay in each case is spontaneous and it is random. It is spontaneous in the sense that it happens without any outside influence. And it is random in the sense that you cannot predict when the decay will occur. You can only talk about the statistics of large populations. So for example, if I had a carbon-14 nucleus, it's going to decay without any influence from anything in the outside. And I cannot predict exactly when that carbon-14 will decay. However, if I had 2,000 identical carbon-14 nuclei, I can say that on average, half of those carbon-14 nuclei will decay in 5,730 years. Or if I have, say, 200 million carbon-11 nuclei, I can say that on average, half of those will decay in 20.4 minutes. Or if I have a sample of lithium-11 nuclei, I can say that half of that sample, on average, will decay in 8.75 milliseconds. If I have cobalt-60, a large sample of that, I can say that on average, half of those nuclei will decay in 5.27 years. And if I have a large sample of radium-226, I can say that on average, half of them will decay in 1,600 years. The times I'm talking about here are called half-lives. The half-life is the time, on average, for half of a sample of identical nuclei to decay. Now let's talk about each of the types of radioactive decay. We'll start with alpha decay. Alpha decay happens when we have a parent nucleus and it decays into a more stable daughter nucleus plus an alpha particle. So parent nucleus just means that's the starting nucleus. That's just the lingo that they use. And then this more stable nucleus that it turns into is called a daughter nucleus. Now the alpha particle is made up of 2 protons and 2 neutrons stuck together. In other words, it's the exact same thing as a helium-4 nucleus, but it's moving at a very high speed when it's emitted. So when emitted as an alpha particle, it's moving on the order of 1,000,000 meters per second. So an example of an alpha decay would be polonium-210. It decays into lead-206 plus an alpha particle. Bismuth-214, it will decay into thallium-210 and an alpha particle. And uranium-238 will decay into thorium-234 and an alpha particle. This first reaction has a half-life of about 138 days, second one half-life about 20 minutes, and the third one half-life of 4.5 billion years. So you can see half-lives can have a range of values. I want to point out something here. Notice that the nucleon number and the proton number are balanced on both sides of the reaction. So the numbers on the top are the same sum on both sides, or on either side. And the values on the bottom are also balanced on either side. So let's say I had radon-222. It decays into polonium by alpha decay. Let's say I don't know the nucleon number or the proton number of polonium. Well, it has to be balanced. So over here I have 222 nucleons. On the right side I have to have 222 nucleons also. 4 of those nucleons are in the alpha, which means that 218 have to be in the polonium. Also, the number on the bottom, the proton number, has to be balanced. The reason it has to be balanced is because of charge conservation. I have to have the same amount of charge before and after. I can't create or destroy charge. So if I have 86 fundamental charges to begin with, I have to have 86 fundamental charges in total on the right-hand side. 2 fundamental charges are in the alpha, which means that I have to have 84 in the polonium. Now, if you're asking why alpha particles exist, why would a nucleus spit out 2 protons and 2 neutrons, a helium nucleus specifically, what's so special about that? Well, it's kind of a long story, but one thing to notice is that if you look at the binding energy per nucleon curve, an alpha particle, this helium nucleus, is a very stable arrangement of small number of nucleons. So it's a convenient chunk to emit from a nucleus. Now, I have way more to say about that, but we're going to stop right there because that's outside of the scope of the class. We're going to move on to beta decay. And there are 2 types of beta decay. There's beta minus and beta plus. In beta minus decay, we have a parent nucleus that decays into a daughter nucleus plus an electron and an electron antineutrino. In beta plus decay, we have a parent nucleus that decays into a daughter nucleus plus a positron and an electron neutrino. Now, let's go over here to the electron. We know what an electron is, and it turns out that in beta decay, the electron that comes out is very high speed. What about this positron over here? Well, a positron, it turns out, is the same as an anti-electron. And what I mean by that, an anti-electron is the antimatter version of an electron. So a positron has the same mass as an electron, but it has other properties that are exactly the opposite. So for example, the charge on a positron is exactly the opposite of the charge on an electron. Electron has a charge of minus the elementary charge. A positron has a charge of plus the elementary charge. All right. Now what about this antineutrino and this neutrino? Well, neutrinos are fundamental particles which are kind of strange. They have no charge, they have no mass, they do not interact with matter in normal circumstances, so when they are emitted, they come flying out and they essentially pass through everything. There are trillions upon trillions of neutrinos passing through you and me at every moment. And they just pass through us and don't have any effect. So they're pretty strange particles, almost like ghosts in a way. But they have no charge, they have no mass. And as you might guess, the electron antineutrino is the antiparticle version of the electron neutrino. Now, why this combination is emitted is kind of a long story. It has to do with something called conservation of lepton number, and it also has to do with other conservation laws, but that's kind of beyond the scope of what we're going to talk about. Now, cesium-137, it turns out, decays into barium-137 by beta minus emission, so it emits the electron and the electron antineutrino. Strontium-90 will decay into yttrium plus beta minus particles. And notice, the upper values, the nucleon number, is still the same on the left and the right. The charge number on the bottom, which we before were calling the proton number, but really it's the number of charges, is also balanced on both sides. So for the strontium-90 decay, I have 90 nucleons to begin with, I have to have 90 nucleons in the end. Well, an electron is not a nucleon, and an anti-electron neutrino is not a nucleon. So the yttrium has to have 90 nucleons. The strontium has 38 protons to begin with, so it has 38 positive elementary charges. So we have to have a total of 38 positive elementary charges on the right. The electron has -1 elementary charge, the neutrino has 0 elementary charge, so the yttrium has to carry off 39 positive elementary charges in order for everything to balance. Sodium-22 will decay by beta plus emission, so this is what the reaction looks like. So potassium-37, it will decay into argon plus the positron and the electron neutrino. So let's think about it. What would the numbers on the top and the bottom of the argon be? How many nucleons would the argon have? Well, nucleon number has to be balanced on both sides, so argon has to have 37 nucleons, and the potassium has 19 elementary charges on the left, so the argon has to have 20 in order for the total number of elementary charges on the right to be balanced. Now, what about gamma decay? So, for example, nickel-60, it can be in an excited state and decay into nickel-60 plus a gamma ray. So notice, gamma rays are photons. They have no mass, they have no charge. They do not change the nucleon number or the charge number on the bottom. So, for example, if we had iridium-192 and it decays by gamma emission, it decays into simply a more stable form of iridium-192. Now, if we look at the alpha, beta, and gamma particles, one big difference in these three different types of radiation is how far they can pass into matter. So I'm going to draw a little diagram here. I'm going to put paper, tinfoil, and a big sheet of lead. Alpha particles are easily stopped by matter. If they impact paper, they're easily stopped by a thin sheet of paper. Beta minus and beta plus, and when I say beta minus and beta plus, what I really mean are the electron and the positron. I'm not talking about the neutrinos here. But the beta minus and the beta plus, they will pass through the paper, and they are stopped by the tinfoil. The gamma rays easily pass through the paper, easily pass through the tinfoil, and even when going through the lead, some of them will pass through the lead. So what we would say about this is that the gamma rays have the greatest penetration. They pass through matter very, very easily and very rarely interact with matter. Alpha particles have the least penetration. They are easily stopped by matter because they will most likely interact with matter. And in fact, alpha particles can really only pass through a few centimeters of air before they interact with the air. Alphas, on the other hand, have the greatest ionizing potential. Means they are the most likely to interact with and damage material. Gamma rays have the lowest ionizing potential, meaning that gamma rays are the least likely to interact with matter and damage it. However, when they do interact with matter, they can have a very damaging effect, even if it doesn't happen very often. So let's think about this half-life again. So remember, half-life is the average time it takes for half of the particles of a sample to decay. So if I make a graph here of the number of radioactive nuclei remaining versus time, at the beginning I'm going to say I started out with some number of nuclei, call it N0. After one half-life, the number of nuclei remaining is going to decrease to half of its original value. And then if I wait another half-life, then half of the value that was left after one half-life is going to be gone. So in other words, I'm going to have 1/4 of my original number of nuclei remaining. And if I wait 3 half-lives, then again, half of the half of the half will be remaining. And so I'll have 1/8 of my original amount of nuclei. And then after 4 half-lives, you can see I would only have 1/16 of the original number of nuclei remaining. Now, if I think about that in a different way, if I think about instead of the number of daughter nuclei that are in the sample versus time, well, at the very beginning, I don't have any daughter nuclei. I only have the original parent nuclei. But then after one half-life, half of my parent nuclei have turned into daughter nuclei. So after one half-life, half of my sample is daughter nuclei. If I wait 2 half-lives, well, I only have 1/4 of my original nuclei remaining, so 3/4 have become daughter nuclei. And then a further half-life, I'll have 7/8 of my sample turned into daughter nuclei. And after 4 half-lives, I'll have 15/16 of my sample turned into daughter nuclei. Now, the next concept we're going to look at is activity. And activity is the number of decays per second in a sample. In other words, it's the rate of decay. And the activity is proportional to the number of radioactive nuclei in the sample, because if you have more radioactive nuclei in the sample, you'll expect more decays to occur, so you'll have a greater activity. But also, and not to get too mathematical, but the activity is equal to the negative of the rate of change in the number of nuclei. Now, this can get us into some interesting mathematical ideas because n, the number of nuclei in our sample, is an exponential function with time. And so if I take the derivative of that with respect to time, well, the derivative of an exponential function gives you another exponential function. So the activity is also an exponential function. And if we were to graph it, it would look like this. If I have an initial activity in my sample at the beginning, after 1 half-life, my activity will decrease by half. After 2 half-lives, my activity will be 1/4 of its original value. After 3 half-lives, it'll be 1/8 of its original value, and so on and so on. So my activity has the same half-life as the number of molecules in my sample. Now let's think about something called count rate. The count rate is similar to the activity, but the count rate is the number of decays that are actually detected by an observer. So if I have a radioactive source right here, let's say it's emitting beta minus radiation, and I have a detector over here which detects a fraction of the activity. Well, that will detect a fraction of it, but that depends on the distance of the detector from the source. It depends on the sensitivity of the detector. It depends on its size. It depends on the penetration ability of the beta minus particles. So let's say that I have a detector and it only detects 1 out of a million decays. Then the count rate that my detector will pick up is equal to the activity of my sample divided by 1 million. Another thing to be concerned about when detecting radiation is something called background radiation. There are sources of radiation all around us. These are called background sources. So, for example, there are natural sources out there which produce radiation, and these natural sources can be long half-life nuclides like, say, uranium-238, which has a half-life on the order of billions of years. Or it could be shorter-lived nuclides with shorter half-lives that are produced by cosmic rays or other natural processes. And there are also artificial sources of radiation, like nuclear waste, or leftover radiation from medical applications, or leftover radiation from the fallout of nuclear weapons testing. But no matter the source, these background sources will be detected by a detector. And we say the background count is what you would detect in the absence of a source. So to get the count from the source itself, what you have to do is take your actual observed count and then subtract out the background count to get the count that is just from your source.